Good evening to all. I welcome you all for the day 3 of AICTE Atal sponsored FDP Artificial Intelligence Edges of Computing. Now I request Ms. T. Darshini ma'am to welcome our session 1 chief guest. Ma'am, please.
Good evening all. It is a great privilege to introduce our esteemed resource person, Dr. N. Narayanan Prasad, an accomplished academician and researcher in the field of computer science and engineering. He completed B.Tech in Information Technology from Pondicherry University in the year 2005, ME in Computer Science and Engineering from Anna University in the year 2009, and PhD from MS University in the year 2017. He brings over 19 years of academic experience, having served at institutions like National College of Engineering, Tirunelveli, and currently working at Vellore Institute of Technology. He has made significant contribution to research with of 30 journal publications, 10 conference papers, and multiple book chapters. Beyond the academics, he has organized workshops, delivered impactful guest lecture, and contributed to funded project with of 21 lakhs. He is also a certified professional in Java programming, cloud infrastructure, and 3D animation. And he is an active member of ISTE and CSTA. We are privileged to have sir amidst us today. Now I hand over session to Dr. Narayanan Prasad sir. Please sir.
Thank you, madam. Am I audible with you?
Yes, sir. Audible.
Okay. Let me upload my PPT now. Just a second. One more time, please confirm whether my slide is visible or not.
Yes, sir. Your side, sir.
Yeah, yes, it's visible, sir.
Okay. Okay. So a very good evening to one and all, and very happy to be a part of this 6 days faculty development program, and I am glad to be part of that. And my topic my topic today is convergence of AI and high performance computing. Okay, what happened? Okay, fine. So during my presentation, I have planned to give an introduction to the high performance computing. And let me see why high performance computing, what is the need for high performance computing, role of high performance computing in AI based applications, Then I will move on to discussing about the HPC architecture. And among this architecture, we'll see about various core components. And one such component is the use of parallel programming techniques in high performance computing environments. And one such parallel programming was the OpenMP. So because at the lowest level, in terms of HPC performance, OpenMP has a huge role. So I'll talk about giving some introduction on OpenMP and then move on to the challenges that the programmer will face while using this OpenMP. So even though it is an parallel programming technique, basically there will be some challenges because if you are not effectively utilizing the parallel programming, and that will harm you in terms of time, definitely. So I'll give you an idea about how to use this parallel programming, which is a base for the high performance computing. Then finally, I will end up with discussing how the HPC performance looks like basically, and how you can measure that. And then I can show some example publications that we had with respect to this parallel programming and what can be possible with that. Okay, fine. So now moving on to the first part. Okay, high performance computing. So the name itself tell you what it actually. So high performance computing. Yeah. So high performance computing is basically a technology which is normally used to solve some complex programs with the help of parallel processing. So here we use some clusters of powerful processors which can handle problems of any size, because nowadays we are using the data sets of very much massive size. So we need machines that can handle this kind of data sets. Okay, and we have to do it in very high speed. So as we know that over the period, how this hardware hardware technology has been improved. We have seen about the statements of Gordon Moore in 1965 that the hardware component cost will increase by the factor of 2 over the period, and that has been happening. Okay, and we have already seen about the Moore's law, which states the amount of computing power available at a given cost will double for every 18 months, and that to happen for a very long period of time. And here too, that is what we are trying to achieve, but in a different perspective. So we are improving increasing the computing power, not only through hardwares, but also with the help of the parallel programming techniques. So that is the mantra behind high performance. Okay. So when I say high performance, basically there you might have machines like supercomputers or HPC clusters, which is offered by so many vendors, something like AWS, IBM, Intel. They are providing various HPC clusters, which we can use it to solve programs which are very much compute intensive in nature. Okay, and how these HPC machines are able to achieve or provide this massive performance, because basically they come up with many number of processors. The many is a very simple term because they comes up with millions of processors, and the performance of these millions of processors are assessed using this metric called flops, the floating point operations per second. Okay. So high performance computing, the term performance is something, it's a very tricky term because um, it is a term which has a different definitions. Okay, because people will come up with different definitions for this term performance. Because for me, performance might have a different value, and for you, it might be a different value. Say, for example, um, maybe if I am trying to travel from Chennai to Bangalore. Okay, and if I'm able to cover that distance in 5 hours, I may feel it is a very good performance. Okay, I thought it is okay. I'm pretty good with that. But if you ask a 20-year-old and give a vehicle to him and ask to cover the same uh, distance in 5 hours, basically, and he might feel it is not a very good performance because he wants to cover that same amount of distance in 2 to 3 hours. And he has a so when you look into this, I have a different definition for performance in that particular aspect, and he has a different definition for performance in that aspect. But uh, our both we both have different requirements for defining this performance. For example, for me, I will not only look on the time that I'm supposed to take, I'm also look on the other factors, how comfort the travel was, how secure the travel was. But that is not the case for the particular the young guy who always think about how to reach the destination in a quickest possible time. So that is where the performance actually lies. Okay, so here I have a very big problem. I have a very big problem. I don't have that much of machines. The problem demands a lot of computations. I don't have that much of memories. That's the basic where the high performance computing comes into the ground, right? So, as I said, the supercomputers are very good examples. They are considered as a large scale HPC clusters. They have been made it with a lot of CPUs. There has been made about a lot of accelerators, which is specified here. So basically, when I say accelerators, we have AI accelerators in the form of GPUs. You have application specific integrated circuits. We call it as ASIC. Then we have FPGA, field programmable gate arrays, are some example for accelerators, which is very common, and that can ensure that the performance can be improved. And in addition to that, high-speed networking fabrics, memory, and storage, and collectively they are going to work together across nodes so as to deliver the best possible performance they can. And also they have to make sure that they can prevent bottlenecks. Okay, that's how things works. It is not changing. Okay, so why high performance computing? So that's the next thing we need to understand. So as we know, the amount of problems that we are dealing recent days is very much compute intensive, as I said, and they demand a lot of computations, of course. And the amount of data that we are dealing with, whether it is any kind of application, it might be modern day, the quantity of data that we are supposed to use for processing that has been increased considerably. And we want to we want to solve the problem as quickly as possible. That is another important factor. And we can use parallel programming techniques, but there is always a limitation where and when to use, whether we are going to use the node level parallel processing, or we are going to use the parallel processing using multiple nodes or with single nodes through multi-threading. So the scaling up and scaling out is also another factor why we demands the high performance computing. So when do you need actually this high performance computing? I can come up with some specific examples where we can make use of this high performance computing. For example, so you are working with an application where you need to perform some time consuming operations in less time. For example, um, just you just think about you are an automotive engineer and you want to design a new car that may consume very less gasoline. So as a part of that, you want to design the entire requirement within very less period of time. So in that case, I cannot go for using the expensive prototypes, which may takes a lot of time, and to check how my design performs when it gets crashed. So I cannot go for using this kind of extensive prototypes. So I can, the simplest possible way is I can go for using the computer simulations, and I can test my design and ensure how it performs. So, so if you have a problem which is very much related to, then that is one scenario where you can use the high performance computing. Then you may have want to perform an operation under a tight deadline. This is very common. This is very common. For example, the weather predictions, and you want to predict everyday weather, and you want to consider a lot of a number of multidimensional values coming out from different sources generated from various devices. You have to consider every bit of forecasting points every day, every minute, and then you have to give these predictions. So that could be another very sensitive applications, which might be which again need a lot of computations. So this is another case where HPC might be very much useful. Okay. Then there may be a scenario where you need to perform a high number of operations for every seconds. Okay. Um, for example, you might have you are running an online application, and you have a customer base, and your server, just assume your customer base gets increased, and your server wants and around 1,000 hits per second. So that means you have to, your server and databases and other related components has to handle 1,000 transactions per second, just for the example. And you need that kind of computing strength. Otherwise, your customers will face very bad delays, and that could impact your business too. Okay. So at the end of the day, what we are looking is we want to run applications very faster. We want to run application very faster. Okay. Basically, if you want to improve the performance, there are only three ways. You have to work hard. There is no, you have to work hard. So when I say work hard, basically how that is possible, you can use some faster hardwares. For example, that can reduce the time per instruction. Okay, how that's possible with us to how the clock cycles are generated. So, but it is a costliest approach because you want faster hardware. So, purchasing these things will uh, always an expensive approach. Then you might have an mechanisms like doing things very smarter. That's what we are doing with the optimization algorithms. So in order to improve the performance, in order to improve the accuracy, we are dealing with the optimization techniques, optimized algorithms, all those things we use. And that is another thing. And finally, if you want to make your application faster, you have to seek for some help. Okay, because you have some resources. If some others provide you more resources, then you can aggregate the resources power and you can make use of it, so that you can just make sure that you execute more instructions per clock cycle. So these are possible ways basically we do, and we try to address all these possible ways in our own style. Okay, I think it is muted. Thank you. So this is what we are trying to do with HPC. So apart from that, there may be some more scenario also. For example, you might have some application which demands a lot of computations, and these computations in turn might need a large amount of memory. Okay, which might not be available with the machines that we have. That is also another case. And there may be a scenario where we have a program that needs to run multiple times, which is very common in the image processing and video analytics kind of things. So we can use a large number of, we can use computing systems, which comes with many number of cores so that you can do this repetitive task in a more flexible manner. So GPU is one best example which can handle these kind of tasks. Okay. And as a whole, I can say in simple words that any program that takes too much time to run, basically, you can come here, you can use the high performance computing machine so that you can try to parallelize the operations and make sure that you can reduce the total time that is needed for the execution purpose. Uh, these are some statistics I just want to show, which is research disciplines, how HPC has been used in multiple domains. What is their contribution? Basically, it was statistics in from 2022, and you could see almost all the major fields they have started using the high performance computing for the research problems. Even though in our country we are lagging a little bit because in other European and US based countries, the lot of HPC machines are available in forum for educational purpose, but in our country we have only the major institutes, and I think CDAC and some premium institutes have their have this kind of machines, and upon request they are allowing us to use. So that is a different scenario. So you could see a lot of domains where they are already in working with using HPC. And another statistics I just want to show the how far the vendors basically they are contributing to this high performance computing environment. So this is not only the related to HPC, but also we know that this parallel processing, the clusters, okay, and these are certain things that are in the market for a very long period of time. So we have some big players contributing in terms of supercomputers and HPC clusters. Okay, even grid computing. You might have heard about the Garuda grid, which is our nation's own, but there are private players who can offer these HPC environments for application purpose. So how does this HPC works? So the concept is very simple as like the parallel processing. So as we know that we have a very big problem, and we are going to divide the problem into n number of tasks. And on the other end, we have millions and millions of the computing nodes which are ready to execute all these tasks. So we are going to supply all these nodes with proper configuration files stating what has to be done and what should not be done. What is the requirement for each and every execution? For example, you want to execute a chunk of code. What is the requirement for the code that needs to be mentioned in the configuration files? For example, you need this much of memory, this much of this kind of resources. So stating all this and providing your task into the compute nodes basically, and nodes will execute. And we have a master kind of thing who will collect the outcome, who will collect the outcome, and what happened, and we will consolidate all the results which have been collected and produced as the final outcome. So basically, it is a very what happens here is a massively parallel computing. It's a very big thing, and this is possible with the help of the HPC clusters. So modern day HPC clusters, we have more than thousands and thousands of nodes, okay, which are part of that. So I have a very simple generic architecture. The slides, you can see that. So HPC applications. So restricting to very less number of application is not fair for HPC. So nowadays, every domain they want this high performance, and every domain who are basically trying to use the various machine learning models or any other artificial intelligence techniques. Definitely, they need this HPC support. Maybe previously, the scenario might be little different because when you have a problem of that kind, initially AI has been used for some initial process, or maybe for pre-processing and for some other purposes, and make sure that AI narrow down the task. Then it is given to the HPC, and so as to infer more insights out of this HPC. But today it's totally different because the ground has been changed. The quantity of information that we are dealing with, the complexity of information that we are dealing with is totally changed. So even from the initial stage that HPC has been used for even for AI-based application, whether it is pre-processing or whether it is and training the data, okay, subject to it satisfies the requirements of uh, the environment. So some applications, so healthcare is something which is very much in the market for a very long period of time. They are using a lot of HPC. Uh, Say, for example, when you take it as the sequence human genome, basically, uh, people might have heard about this. The first time that the researchers has been took around 13 years to sequence a human genome, but now the scenario is totally different. So within a day, it is totally possible. This is because sequencing the human genome involves various activities. For example, you have to extract the DNA from the cell, and you have to cut it into different fragments. You have to sequence it. It means you have to read one base at a time with the help of this sequencer. So there will be 3 billion base pairs available. So how many base pair you are using, it's up to your application requirement. Then you have to go for analysis. So it is basically a very hectic and compute intensive task. That's why it takes a long period of time with the traditional computing machines. Okay, but now the scenario has been totally changed. Okay, and media and entertainment, of course, we used to watch live games, and HPC's clusters that has been utilized there will provide you the necessary speed that is basically required to stream all your live activities and also generate the highlights during the live activity itself, and that can be used then and there to make sure that the audience get entertained. And it can also be used for rendering 3D graphics, adding special effects. And people used to watch the cricket matches. You could see along with the regular live matches, so many other special effects. They will include so many other a bit of activities taking place here and there. They will try to include statistics. They will try to bring, which includes the current activity too. So all these things are basically possible with these high performance computations. Okay, we do have one work related to this. And then we have the banking and financial services. People might heard about the algo trading recently. So you have the AI bot embedded, which will help you to give you very good recommendations. And to give that recommendations at live real time, you need to process huge amount of data where the HPC provides its supports. Weather forecasting, automotive industry is another area where you can where HPC used for very long period of time. Basically, okay, you can use HPC to simulate various activities. For For example, you can use it for designing the products or process. You can use it for designing the aerodynamics first to reduce the air drag and frictions. You can use it for battery simulations to make sure that you can optimize the battery performance. You can maybe from the maybe from the safety perspective also you can able to ensure through these kind of simulations. So finally, you have the cyber security is another important factor where where we need the defense people to understand the various patterns that has been used and in order to mitigate the system from any kind of cyber attacks. So again, there is another application where HPC was very much used. The role of HPC in AI-based applications. Yes, of course, as I said a few minutes back, previously it was AI, then HPC. So now they have been bundled together. And because modern day applications demand more computation powers, they need more resources uh, for training purpose, deploying purpose, and even for scaling purpose, you need this kind of HPC support. Some examples that might justify the need is something. So if you want to train the model, and you can do it. How you can do it? You can distribute the computations across the thousands or lakhs of nodes that we have, so that they can do it in parallel. So the training time can be reduced considerably. So you can use it to handle massive data sets in parallel. You can use it to reduce the, you can use it to simulate the environments, basically. For example, to generate some synthetic training data, to create some realistic scenarios so as to be used for some learning purpose. Even it can be used for the hyperparameter optimization purpose. So we know that the hyperparameters tuning process has been used to improve the accuracy part. Then when that can be done so as to get a very the optimal level of configurations for these machines. So big data is another area where the HPC is very much used. Okay. And AI applications, we know, generate a huge amount of data. So HPC provides some high-speed storage to support that. That's very important. And in addition, with they also provide you and very efficient pre-processing support so as to accelerate the data cleaning, normalization, augmentation process. So as a whole, nowadays you cannot say it is two different terms. It is normally people used to people using the term AI accelerated HPC is very common nowadays. And it is also we are also moving towards some hope you understand. Hope we are moving towards this exascale computing, which is also contributing for heavy workloads that AI is supposed to face. Understanding the challenge of AI in HPC. Of course, we are trying to use this AI with HPC, and whether they can embed it well, of course not. They have their own characteristics. So you have some challenges to accommodate that. Okay, maybe in terms of scalability, in terms of energy efficiency, because we know AI training is very much energy intensive, and how HPC can handle that is another challenge. And managing the heterogeneous architectures is again a major challenge. And well beyond that, there is always a bit of so very sorry, I have muted some conversations. So there is a trade-off between AI and HPC requirements within the CPU architecture. So what kind of trade-off? So for example, if you look into the AI, okay, so they can compromise the amount of cores that can be used in order to achieve the speed. Okay, they want to use the optimal amount of cores, whereas the HPC workload expectation is totally different, basically, because HPC workloads will always prefer greater compute performance with a high core count. So, and this needs to be effectively managed. Okay. And also the performance bottleneck is another challenge when you are using AI with HPC. Okay, because the requirement of resources might vary. For example, the memory requirement will be totally vary. So, and HPC has been we could have some we have some uh, just a minute. Okay, we have some big players who are offering some. I think AWS is giving some services in order to handle this memory constraint exclusively. I could have forgot that name of the service, but it is explicitly used for this AI accelerated SPC. Whenever there is a memory constraint, then that kind of services can be used effectively. And the level of complexity, yes, that is a very important point. Okay. So embedding AI with HPC, basically you need trained person who can do well with both AI as well as the HPC, which is very difficult to find those peoples. So moving on to the next level, which is HPC architecture. So this is a very simple generic architecture which I have used for my slide. And when you look into this architecture, basically there are three primary components as like any execution environment. You have a compute, you have a storage, and you have a network component. So to start with this users, basically you have this user part, okay? So they will try to log in into the one of the node in the environment called a head node. Okay. So the head node is the entry point where user will try to log in to access these clusters. So basically this is a HPC cluster, for example. So user will try to log in into this cluster through this edge node by using some SSH client program. They use these CLI commands to interact with the computer what they actually want. So whenever the request received by this particular head node, so that will be directed to the scheduler. We know scheduler is basically a job management system. And basically, there are two types of scheduler we have. Okay, we have two types of scheduler. You have a batch scheduler, and you have a lightweight scheduler. Lightweight scheduler. Pen is not good. Fine. Batch scheduler and lightweight scheduler. So how you are going to handle the workloads is what this scheduler, the type of scheduler deals with. Batch scheduler, say for example, I have some example batch set is something like HT Condor. People might have heard of this. HT Condor is there. The Oracle Grid Engine is there. Slum is there, very famous scheduler. They are all an example for batch schedulers. So they treat workloads in a batch. Then you have a lightweight scheduler, basically. Okay. So some examples for lightweight scheduler, basically Falcon is one example, Sparrow is one example. So they treat workloads, okay, in a, so we are not going to consider the entire workloads in terms of batch. We are going to take task by task and process it accordingly. Maybe the allocation, the scheduling plays a vital role in classifying these batch as well as the lightweight schedulers. Then we have a core part here, which I am just circling is the compute nodes, okay, which is the compute nodes. So this is a regular compute node, or you can call it as an HPC cluster also. That is not right. Basically, there will be 100,000 nodes is very common nowadays in this particular part. Okay, and these nodes are responsible for the execution of the task. Okay, so scheduler will schedule the task, and the compute nodes will take care of that, and they are responsible for the parallel processing. So how this parallel processing takes place basically? So within a node, you can have a shared memory interconnect, and parallel processing is possible within the node, and that will happen basically. Let me check again. Okay, that is possible basically with the help of OpenMP. Or you can also have a parallel processing, which is basically possible through the use of multiple nodes. It's something like a distributed environment, parallel processing in a distributed environment. Then for that, we can use a parallel processing interconnect, which is called MPI. Okay, so which is a message passing interface. People might call it as Open MPA also. So OpenMP is open multi-processing basically, right? So we have two parallel programming tools, which is used by almost every supercomputers for parallel processing purpose. And here, this OpenMP is basically used by the single node to ensure that will be parallel processing with the help of shared memory interconnect, where MPI is ensures the parallel processing between by use of more than one compute nodes. Then you have the storage part. So again, you can have three types of storage. You can have a physical storage, and which might be in the form of storage area networks or network attached storage. So uh, you might have NAS, or you might have, don't think what happened to the pen. Okay, it might have a SAN storage area network, or the for a common people very commonly use storage the cloud storage. So when you have this cloud, then scalability is not a factor. If it is a physical, then scalability is one constraint or one limitations that we have in. Okay, but when you go for cloud, it gives a very high degree of scalability as well as the flexibilities. And but if you look into the modern day supercomputers, they are just using the hybrid approaches. So based on the need, they are just moving on to using both physical as well as the hybrid. Then the final component, the core component, is the network. Okay. In simple, we have lot of nodes, and all these nodes needs to be interconnected with a high performance and low latency networks, so that we make sure that all these workloads will give you a very optimal performance. So uh, some networks like infinite band can be used for this purpose. Okay. So apart from this compute, um, apart from this compute, storage, and network, and there are a few other components which act as a backbone, for the high performance computing applications. So for example, there are parallel computing frameworks, which I talked about. I have talked about the OpenMP MPI, and we have accelerators in the form of CUDA, sorry, GPU, and we have the optimization libraries. It varies to the type of HPC that we are embedding, and which helps you to utilize that to optimize your process. Then you have these workload managers. Workload managers are nothing but the schedulers. Okay, it is nothing but schedulers. Okay, I have talked about the schedulers. So my intention here is what is the key role that this parallel computing frameworks plays in executing these modern day high performance applications. So why I have taken this particular stand, because if you look into this graph, which I take it from the LLNL website, which is high performance compute. They offer high performance computing workloads to their people. So they have stated that over the period, especially in the past 20 years, you could see, okay, maybe with the help of faster networks or distributed systems or multiprocessor computer architectures, you could see to what extent, okay, the performance has been improved. Okay, so we are talking about the exascale the operations. So you could see over the period it has been improved quite a lot, and it's keep on moving. The statistics is up to 2022. So that's why we used to state very clearly that parallelism is the future of computing, even though it is very old. But uh, without parallelism, it's very simple to say that HPC is you cannot function the HPC. HPC is nothing there without parallelism, right? So parallelism is the future of computing. We try to explore different ways so as to improve this parallelism. Of course, there are challenges. Of course, there are challenges, but they are addressed over the period of time. Okay. So as we tend to see, this parallelism is very important, and to understand a little bit more about this, okay, uh, let me see this particular an example HPC machine Fugaku. So people might have heard about a lot of supercomputers. Not only Fugaku, you have Summit, you have 10-way Taihu Light, lot of supercomputers there. I just taken this one as an example, and in order to understand its size, okay, you could see that it has around 158,000 nodes. This is enormous. Okay, so how these nodes are packed up? Basically, you have a CPU here, and then a pair of CPU. Okay, you have a pair of CPU. Uh, this pair of CPU, basically we call it as a CMU. Okay, and CMU, central memory unit, basically, which has two CPUs. Then a collection of these CMUs will form a BOB. So collection of these CPUs, it's form a BOB. That is nothing but collection of blades, bunch of blades. So in this case, 8 CMU will form a BOB. That means there will be 16 nodes, because one CMU will have 2 nodes. Okay. Then after that, you could see you have a shelf, okay, which consists of nearly 3 BOBs. It consists of nearly 3 BOBs. So the number gets increased. Then you have the racks. Then you have the racks. Okay. And in our case, the rack has nearly 8 shelves. Okay. And as a whole, you could see we have around 1,58,976 nodes. So you can achieve very high degree of process. Even in each node, you have multiple processors. That's a different thing. Each node have a multiple processor, and each processor in turn can work with multiple threads. So the degree of multi-processing is something unbelievable. So here, as this Fugaku is a petascale supercomputer, as per the 2020 top 500 list. So top500.org is one website where you could see the list of supercomputers. They might be ranked these supercomputers with respect to this CPU speed. They use some benchmark tools, something like HP, LinkBack, similar kind of stream, similar kind of benchmark tools they use so as to assess the performance, the theoretical floating point operations, and they might rank these supercomputers every year. So here, there's a little bit of history about this, but the point I need to note is the parallel programming models that has been used by this particular species. So they use this XMP basically. Okay, so so XMP is nothing but the scalable multiprocessing. This is the customized version of an OpenMP. It's a base for everything, and they have already used MPA. So similarly, if you take any other machine, for example, you have a Smith, which is an IBM-made GPU accelerated supercomputer. Even they used MPA for compute node communications. That machine has nearly 4,000 plus compute nodes. So the communication between these compute nodes takes place with the help of this MPA. MPA is message passing interface. Whereas OpenMP is used within the nodes to parallelize the task, okay, and across the number of cores that we have. So this tool plays a vital role at the lowest possible level for achieving the high performance at the highest possible level. So that's why I am just focusing this parallel programming models. Okay. So I just move on to the OpenMP part. Okay. So what is this OpenMP? So OpenMP is a parallel programming model which is very much suitable and very easy to use for any parallel programmers, and we can use it to exploit parallelism within the nodes shared memory that we have. So since it is OpenMP and it is a standardized multiprocessing API, so it has been used by vendors across the world who are working on parallel programming. It is multi-thread based and it is expressly used in shared memory environment. So the primary goal of this OpenMP is to provide a standard and portable API for writing shared memory parallel programs. Okay. So some of the benefits, it's a standard among the various shared memory architectures. It's used by the parallel programmers, can be easily understood by everyone. And it just provides the capability to write the code in the incremental version. So which makes the programmers easy to build. Multi-threaded base, people are very much aware about threading concept, so very easily we can able to understand what actually it is. And it can be embedded with some high-level languages, for example, C, C++, and Fortran. That's why we claim it has a very good portability. Okay. So we have a group of members who are taking care of this OpenMP who used to release the various versions of OpenMP. Okay. And there are some open forum where we can be a part of this OpenMP too. So at present, the OpenMP 5.1 is there. Then moving on, just moving little bit deeper into the OpenMP, because it provides the parallel processing. So we can able to bring this parallel processing from in a lighter note, and how a simple programs can be parallelized is what I am trying to discuss in the next 30-35 minutes, right? So there are three core components basically OpenMP has. So you have a directories, which is basically an assembly directive, and you have a runtime library routines. You have a lot of library routines which can be used so as to uh, simplify the coding prospect. Environmental variables will help you to control the code during the runtime. So and there are some environmental variables, default variables are available. Now, what is this directives? So it is basically it's a directive-based approach. OpenMP is a directive-based approach. Okay. So when I say directive-based approach, along with your regular code, so we are going to use this assembler directives, and this directive will instruct the compiler how this code has to be executed, whether this has to be executed in parallel or it has to be executed with how many threads, and how you have to deal with various OpenMP constructs. So it gives the direction to the compilers, these directives. Okay. So one example for this particular OpenMP directive is hash pragma and OpenMP parallel. Okay, so hash pragma is something very common in it is a keyword to be used in OpenMP constructs. OMP says it is OpenMP, and parallel is the name of the construct. It is one example directive. It is a name. Okay. Then one example for library routines is, for example, OMP underscore get underscore num underscore threads. So this will return the number of threads that I have, okay, that this region of code has, how many threads I'm going to use to execute. And I have one more approach called environmental variable called OMP underscore num underscore threads. So it says how many threads I'm going to use to execute this particular section of code. So for example, in this case, I have set it as 8. That means I use 8 threads so as to uh, execute the particular shared region. So this is the generic code. This is a generic code structure. So to start with, okay, so here I'm not going to discuss the entire OpenMP code. My intention is to show you the basic code and what problem that actually a parallel programmer will face while writing the parallel programming code. Because uh, the main intention of using this parallel processing is to save time. Okay, but unfortunately, if you are not using this construct properly, what happens? You are going to waste a lot of time in execution. Okay. So what mistakes people may make very commonly, and how tricky this construct was. So I want to take some sample scenarios and show how these things has to be handled. Okay. So say for example, and this is a OpenMP header file, and when there is a main, so you have a very sequential execution. We have a sequential execution. Okay. When we have main, so that means only one thread will start executing whatever code I have in this particular page. It will be executed by only one thread, which is T. And here is the start of the parallel region. So that means, and here I will generate n number of threads, and whatever code that is available within this parallel region, it is a parallel region. So whatever code I write will be executed by multiple threads. Okay, it is executed by multiple threads, right? Then once this region gets over at this point, then you rest of the portion we call it as a serial code. We have only one part. So how it actually looks? Let me make a very simple program, very simple program. Then we move on to the problems. Okay, for example, so what I do was just printing a statement, a very simple statement, printing a statement here. Okay, and here what happened, I have necessary header files, and this is the parallel region which was created. The OpenMP construct which I used was parallel, hash pragma OMP parallel. So as I said, anything which is written in this code will be executed by multiple threads. So however, in this case, I have not specified any threads. So what happened by default, okay, the number of virtual processors that are available in the machine will be considered as threads. For example, if you can go and check it in the task manager to ensure how many virtual processors you have. If you have two, then these two threads are generated here. Okay, that means this particular code will be executed by two threads, so that you get two executions. Okay, that is what's happening here. And if needed, I can specify the number of threads. I can specify the number of threads with the help of an environment. There are different ways, but here when I execute this program, I use a environmental variable which is called omp underscore num underscore thread, and I have set this value as 4. That means I am defining here that I want this parallel region to be executed by 4 threads. That is the reason. So what happened here? Okay, I have 4 threads, all 4 threads executing this particular part. Okay, this is how things works. Okay, this is how things work. But what is the challenge here? Okay, there are numerous challenges. Let me address some common challenges. Okay, so I'm not going to explain the same thing again. The header file, everything is there. So when you look into this code, basically this is the parallel region part. Okay, so hash pragma omp parallel region part, and let us assume that my machine has 4 virtual processors. That means this code will be executed by for 4 times. What is the code says? So omp underscore get underscore thread number. Whenever a thread execute this particular function, okay, omp underscore get underscore thread underscore num, this function will return a thread ID. So that means every thread has a unique ID. Okay, and whenever a thread executes this particular function, then it is going to return you the thread unique ID. So it is a unique integer. Okay, so and whatever ID I have received, I'm going to print it here. I'm going to print it here. Very simple. I'm going to get the thread ID and I'm going to print it. So I have 4 threads. 4 threads will try to execute this particular function. Okay, and it will try to print its own ID. But if you see this output, that's where the problem actually challenge comes. Okay, and there is a root cause for various problems. You could see, and hello of one sense, it is first thread has printed hello, then 0 thread, then first thread printing well, then 0 thread. So what it says actually, okay, the order in which the threads execute the parallel region is not defined. The programmers has no control, okay, on the order in which the statements will be executed. So that means you cannot control that. So it is implementation specific. The way in which the thread has been created and it is scheduled by the OpenMP implementation specific, the thread will execute the statements one after the other. So in this time, I get the input of this particular combination. Okay, this particular combination. When I execute the same program once again, I'll get some other combination because I don't have any control on how this program will be executed. Okay, so because of this aspect, what happened? This aspect will reach to the race conditions. So one major problem with the OpenMP is the race conditions basically. So this race condition might occur because of the order in which the programs are executed. Okay. So this figure tell you how the OpenMP works. So you have the initially serial part. In there is a parallel region. Then you have the multiple threads part. Okay. Then after the end of parallel region, it's over. Then you have the serial part. Then you can, if you have a parallel region, then I can have multiple threads. Okay. Then at the end of parallel region, then I will have only serial part. So in a program, you can have any number of parallel regions. Okay, you can have any number of parallel regions. So it depends on your application requirement. Okay, there are different ways this number of threads can be assigned. For example, this is one way. I'm using a runtime function, and I can use that. So I'll go to the next problem basically. So what happens if there is a function? Okay, you could see there is a function here, and suppose I had 4 threads. Okay, so what happened? A 4 copy of this function call. Okay, the function will be assigned to each and every thread. So that means each and every thread will take a copy of the function and it will execute and it will return back the results. So this is a very good figure. So I have 4 threads. So they are going to handle this. They are going to have this copy of these functions, and they can do their own executions. Okay, and for example, if I have, if I want to say, for example, if I want to find sum of n numbers, okay. So what I can do is I can divide this operation into 4 threads, and I can give each thread the n by 4 amount of operations so that they can work in parallel and they can return back the results. So this is how the parallel processing works. A simple syntax for the parallel construct. Yep. Normally, parallel is a derivative. It comes with some classes. These are the example classes, and I'm not going to discuss about these classes. But what classes are is basically they can give some additional features to this particular directive. So classes will give more meaning. It can give some additional meaning, some additional features to the available directives. So there are n number of classes available, and OMP parallel will support some limited number of. For example, you have a private. I can create a private entities. I can create a shared entities. I can create default entities. Okay, these are some other things, and let me move on to. Okay. So let's take this example program. So I want to deal with this example program to make sure there are a lot of problems embedded here. Okay, fine. This is the OMP parallel section. Okay, and this is a straightforward program. So what I do was I'll tell what this program and what are the problems that we naturally will do while writing these programs. Okay, so here we have a parallel section, and I have a function called OMP underscore get underscore num threads. So it will return the number of threads. Numt is a variable. Okay, numt is a variable which will return, the thread will return the number of threads. For example, here it is 4. And another variable is called TID. Another variable is called TID. So this is nothing but thread ID. Whenever a thread executes, it will return its own ID. So here, let us assume I have 4 threads. Okay. And any variable which you declared inside the parallel region, this becomes a private variable. So that means for each thread, for example, T1, T2, for example, they get a separate memory space where they can store their values. For example, when T1 comes with respect to numt, it has its own space. And with respect to T1, the TID will also get its own space. Okay. And T2 for numt it has one space, and for TID it has one space. Let's say this is numt and this is a TID. So what happened, since it is a private variable, so every thread, okay, in order to store their respective variables, okay, they get a private memory space. Okay, and okay, so in this case, when they get this private memory space, there is no problem because whatever value they retrieve, they are supposed to get. For example, numt will give you the value 4. Whichever thread comes, it is going to return the value 4 because there are 4 threads. And this TID will return for each thread, it will return its appropriate thread ID. For example, 1, 2. So depends on its thread ID, it will return the corresponding ID. Okay. So now where is the problem actually? Okay. Let's see the problem one after the other. Okay. So in a step 1, what I did, so in the previous case, what I did was both the variables are declared inside the parallel region. You could see it was declared inside the parallel region. But now what I did was I have brought the declaration out of this parallel region. So when I declare a variable outside the parallel region, that means in the serial region, this variable becomes a shared variable. This is a shared variable. So this is for numt and this is for TID. Okay, let's assume this is TID, this is numt. N means numt and TID. So any thread which executes inside this parallel region, they will use this common memory space. They will use this common memory space. For example, if thread 0 comes, it will execute this particular statement numt equal to omp underscore get underscore num threads. It will return the number of threads. So it will store the value 4, for example. And TID, then the same thread. For example, if it execute TID equal to omp underscore get underscore thread underscore num, it will return the thread ID. So it's since T1 comes first, okay, the value 1 will be returned. Then it can print its value. Okay. So likewise, every thread will try to execute and they will just override these values. So n, as far as n concerns, any thread comes, it is going to write only 4 because OMP get num threads will return only 4. But as far as this function concerns, get num thread ID, thread number, according to the thread, it will return the thread value. So when a thread comes, when the thread 1 comes, the TID value becomes 1. When thread 2 comes, its value becomes 2. Okay, so there will be overwriting of values in the shared memory. Okay, so now if you see this output, so I have already executed and kept the output. If you see this output, basically, okay, you could notice for the first time, the output you couldn't find any mistakes. But in the second output, you could see that thread 1 has been logged twice. So why this actually happened? That is a question here. So the reason for this particular, because this is a wrong output, basically, you cannot have an output like this. But why we have such a kind of output? So this is because basically, okay, let us assume when thread 1, okay, let us assume when thread 1 executes these 2 statements, and once it has executed these 2 statements, and with respect to thread 1, the value will be 4 and 1. Okay, and immediately the thread 1 has to execute this print so that it can print both the values 4 and 1. However, if T1 before executing this print statement, let us assume the next thread has executed these 2 statements. Okay, say for example it is T2. Okay, so once T2 has executed this statement numt is always going to be 4 because that is total number of threads. But when T2 executes this particular function omp underscore get number thread number, it will return the value 2. And this 2, okay, will be overwritten because they are managing a shared memory space. So when in the shared memory, okay, the value written by T1 is 1, which is overwritten by the thread 2, whose value is 2. And meanwhile, the thread T1 is trying to print that particular TID. Okay, so as a result, and a T1 will try to print this TID, will get the value printed will be 2, which is not correct. Okay, so this happens. Okay, this happens because we have no control on how these threads has to be executed. We have no control on the order in which the thread has to be executed. And secondly, a delay here, a delay at this particular point, okay, will always has caused the issue. Okay, has caused the issue. So now, in order to understand, okay, a very simple solution, you have a very simple solution, because if you make this the TID variable as private, the entire problem is solved. That's it. Okay, it's a very simple solution. Okay, when you make this TID as private, the entire problem is solved, right? But however, we want to explore a little bit more, okay, to understand what is actually, whether this is actually a problem or not. So in order to explore that, so please make sure that the statement which is marked in red color is the one which is updated from the previous slide. Okay? The statement which is marked in red color is the one which is updated from the previous slide. Okay. So now what happened? I have introduced a loop here, which is a very big loop. It demands nearly a
Sir, disconnected or what, sir?
microphone is muted. Okay, I have been removed from the group. So I am joining now. For the time being, I will make it little fast. Okay, I have a entire window I will share. Okay, can anyone confirm me whether the screen is visible?
Yes, sir, visible.
Yes, sir, it's visible now. Thank you, sir.
Yes, sir.
I don't know. I have been kicked out of the presentation. For example, 3 is where I have starts. Okay, so you could see here, the simple solution here is using the price. Just a minute. I will. Okay, fine. Now it's fine. Okay, so the simple solution is I have made it as a private, the TID as a private, and numpty as a shared. So what happened here, when it becomes TID as private, every thread will get a separate space, and this problem, the problem which you have seen, can be easily eliminated. Okay. Now, in order to understand whether it is really a problem, so I want to introduce a very long wait here, okay, to see whether this is actually a problem. So in order to understand that, what I did was I introduced a very big loop here. Okay. And what happened, say for example, I have 2 threads. Okay. I don't want to go with 4. Here it executed with 4. I take 2 threads. So when first thread comes, it executes this numpty and TID. Okay. And what happened here, it will wait, because TID is declared outside the parallel region, which is serial. So I have a shared memory, which is in the form of numpty and TID. Okay. So when thread 1 comes, it will execute this particular statement, and it will this function will return the value 2. So the value becomes 2. And when it executes the second statement for thread 1, so this function will return the thread ID as 1. Okay. So then it encounters this particular loop. It is a very huge loop, so it has to wait for a very long period of time. Now, meanwhile, thread 2 comes and execute this statement. So it will return the same value 2, so no problem. Then when it executes the second statement, the second function, this will return the value 2 because thread 2 ID is 2. So this will override the value 2. So we understand this is a problem. Then when first thread completes this loop and comes again and print this, it will print the value 2, 2, which is not correct. So we understand this is a problem exactly. So when you introduce a long wait, okay, the parallel processing is really suffering. Okay. So the simple way is to use this, make this shared variable as a private variable. Okay, so it works. You could see both the execution, they are correct. Okay, so now we'll try to see some other problems here. What I tried was I can optimize this code. So if you ask, it is giving you the output, but can you say this is an optimal code? No, because I can optimize the code so that, because every statement will consume some amount of time. So if you are able to optimize code, we can save a lot of time. That's another factor. So here the problem is, you could see here, this is a function omp underscore get underscore num threads. This function will return the number of threads in the parallel region. So whenever a thread comes, whatever the thread, it is going to return a same value. For example, if you have 4 threads in the parallel region, when all 4 threads execute this particular statement, it is going to return the same value. Then why I need to execute this particular function 4 times? So that is a problem here. Why I need to execute this statement for 4 times? If I am able to make only one thread execute this statement, then I can save a lot of time. So in order to achieve that, what I tried was, okay, I just declared this numt outside the statement. I just tried because I need to execute only once. So what I thought was, if I put it in the serial region, so this is a serial region, and this is a parallel region, and I put this when I put this code in the serial region, basically what happened?
Sir, the slide is not visible.
Slide is not visible.
So slide you're explaining is not visible actually. You have to scroll the slides, please.
So it's visible for me. I'm writing here as XY. Is it visible? XY.
No, sir. No, sir.
No, no.
Sir, when to use HPC, that is visible. That slide is visible only.
Okay, I think then I have moved a few more slides. Okay, I'll share it again. Is it visible now? I'm moving this slide.
Yes, sir. It's open
Yes, sir.
MP.
Yes.
Yes.
Are you able to see example 8? Is it fine?
Yes, sir.
Example
Yes, sir.
8. Okay.
Yes, sir.
Thank you. So what I tried here was, okay, rather than, see, I'll come again here. So here what happened, okay, this particular function was executed by 4 threads, okay, and still all 4 threads is going to give you same output. So I can optimize this code to make sure that only one thread can execute this particular statement or this particular function. So keeping that in mind, I tried a way to keep this particular code out of this parallel region, and that is keeping it in serial region and see how it works. But here, since it is in serial region, the number of threads is going to be only one. So that is a major drawback. Okay, so this is not a right approach. So I am going to use a very simple way using an if statement where if thread ID is 0, then you can execute this particular statement. Okay, this particular statement is going to, this particular function is going to return value, and this part will be executed by only one thread, that is thread 0. But when you see the output, okay, you see the output 1, it is fine. But when you look into this output 2, you are not getting the right output. This is because, as I said already, we don't have any control over how the thread will execute this particular parallel section. So what happened here, you could see here, the thread 1 and 2, see the output, second output, thread 1 and 2 is giving in some garbage value, uh, and 3 and 4 is 3 and 0 is giving the right output. This is because we made sure here only thread 0 can, okay, execute this particular function, and only if the function get executed, the numpty value will be enabled as 4. It will be assigned as 4. Okay, but what happened before thread 0 executing this particular part, thread 1 and 2 has already completed its task, and they have executed this print statement and without having the numpty value, and that's why you are getting the garbage approach. So this is the problem actually we have. Okay, so these are some example problems that I do have, and these problems can be solved basically using some synchronization constructs that are available in the OpenMP. So we call it as synchronization constructs. Okay. So these constructs, for example, barrier. This is one example construct. So barrier will ensure that if you have 4 threads, okay, at this point, only if all 4 threads arrived, then only it will allow the threads to further execute. Okay, this is one mechanism which is available in OpenMP. So comparing to other parallel programming mechanisms, OpenMP have a very rich set of synchronization tools. Okay, so similarly, you have another synchronization mechanism called critical. So this will ensure mutual exclusion. That means it allows only one thread, so that these kind of problems can be eliminated. Okay. So I just stop here. I will go to the last part of HPC parallel programming. So if you see this parallel programming performance, so OpenMP is something, a very big version, and I have kept, I hope I have given some glimpse about that. And when you are not using this parallel programming construct properly, then you are going to waste your time during the execution. So it's very important that we use the constructs properly. So performance of the parallel programming is depends on the amount of code that can be parallelized. Okay, so you need to have the job. You need to have the amount of code, and the code should mostly it should not be dependent. It should be an independent one basically. Then it is very good for parallel programming purpose. Okay, and basically if none of the code was parallelized, basically the speed up was considered as 1. There is no speed up. It is basically a sequential execution. If you are able to parallelize 50% of the code, then basically the speed up is 2, right? And if you are able to do more, and you can achieve more degree of parallelism. So the programming performance is based on two factors: the number of compute nodes you have, and based on the quantity of task that basically we are using. Okay, so this figure shows when I'm using 10 processors, how much speed up I was able to achieve. 100 processors, 1000 processors, 10,000. It is an output of some execution. So you could see over the period, even when you increase the number of output, in number of nodes, that compute nodes, or in simple term number of processors, the speed up has not increased. This is because the task is not supporting. The task is not supporting. For example, if you have two-person is enough to carry that. Even if you have 4% or 20%, the performance is not going to improve. So this is what I want to convey. And some performance metrics are there. This is a very simple way to measure the performance of high performance computing. So for example, first you have to analyze the floating point operation that has been taking place per cycle, the number of cycles executed per second, then per socket. Then here we come into the hardware part, how many nodes we have, how many racks you have, and as a whole you can get the floating point operations per second. But for supercomputer, this is a way that we can use to some extent. But supercomputers, there is a website called top500.org. Okay, they will use some benchmark, okay, benchmark tools. For example, HP LinkPack, okay, LinkPack or some example. What they do, they will give some heavy workloads. It might be linear equations or floating point operations, whatever it is. And based on that, they analyze all these supercomputers and they will release the rank every year. So you can visit this website, top500.org, to get to know about that. Okay. And if you want to measure the flops for your machine, because nowadays they have machines with GPU, then this is the very simple equation we can follow to understand the performance. Okay. So I hope I have reached that time. I have went beyond that. So I'll stop here. And if people are interested, you can please contact me. We can work more on that. So we have some publications which uses this or based on this OpenMP and the MPA. You can check it out in maybe in Google Scholar or Scopus kind of things. Fine. Thank you.